Hello everyone, we are back again. What we want to do today is demonstrate one of our in-house services, which is balancing. This is of course balancing the rotors on their own axis and balancing the rotating assembly. Some of the things we're going to talk about will show you different types of rotors that have been modified that are candidates for balancing. And we will show you modifications that will change balancing requirements dramatically versus some that you can do away with. But we obviously always recommend balancing after, so we'll show you all the varieties of situations where we would recommend balancing, and we'll give you some close-ups of the rotors and then doing the corrections on the rotors. And then once we have the rotors done on their own axis, we'll show you how we weigh up the bob weights and mount those to the E-shaft, and then do the counterweight corrections as a rotating assembly. Okay, so stay tuned and we'll see you soon. Okay, so these are some samples of rotors that have all had work done to them. Starting from sort of the least significant modification that will affect whether or not you need to balance, all the way up into lots of different individual modifications on the rotors where you would have no choice but to balance. This rotor here would be an example of something where we have resurfaced the face for clearancing and then also done the clearancing on the tips. Now, some people have asked us, if we just do clearancing, do you need to rebalance? Well, good question. And I would say in this particular case, because we are taking off material symmetrically off the tips and symmetrically off the face of the rotor, it is probably not a fundamental to need to rebalance. Would you notice on a balancer? It's possible the rotating assembly itself may pick up the fact that these rotors have become lighter in respect to the counterweights. But if you just spun this rotor on its own axis after just clearancing and then tip clearancing, it is likely you would not see that the rotor would need to be rebalanced. But we always like to check them, and we typically recommend that even if it's out by a gram, we bring it back to zero, and then you know for sure it's perfect. Another modification that's been done to this rotor, it's tough to see, I don't know if we can zoom in here, but this is combustion chamber clearancing. And this is a modification that we do for high RPM and high boost and just high horsepower in general. So when you get any crankshaft deflection, you don't have to worry about the rotor actually hitting the chrome on the rotor housing. And usually you'll see this will touch at the 3 or 9 o'clock point on the housing if you do have a problem. So we remove material around the combustion chamber only. Now again, a good question would be, well, if we're taking off material symmetrically on all three sides, is that going to change the balance of the rotor on its own axis? The answer is, if you get lucky and the machining is taking off very equal amounts of material on all sides, you could spin this rotor with either just the combustion chamber clearancing mods or the face clearancing and the tip clearancing combined and get lucky and see the rotor is at zero. And if it's a zero, you don't have to touch it. If it's out, then you have the availability to correct it because you know where to correct it. As a rule of thumb, no matter what you do, it's a great idea to check. Can you get lucky? Yes. And is it a requirement to rebalance? Well, you'll never know until you check. But if you just were somebody who's a gambling person who wanted to take a risk and attempt to throw the rotors in, again, where you're going to notice the problem is once you've removed material here, 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 and on both faces, you now have a lighter rotor, which is going to mean that the counterweights are going to need to be corrected. So we will show you as we go, when we spin the rotating assembly as a whole, what kind of differences you will see respectively front to rear counterweight based on the mods that have been done to the rotors. Now, the sample that we're going to deal with today is going to be these rotors that were sent to us by a customer, which have heavy modifications. So these have, let me grab this one. These have big scallops for the intake ports, okay? And that's in, again, symmetrical locations on the rotor, but only on this side of each rotor. No doubt about it, this rotor is going to need rebalancing just for the sake of the scallops. Also, this rotor has been lightened on both sides. No question about it. We have to rebalance this. Now, let's just say we were dealing with a rotor that's just lightened. So let's grab one of these. This is a rotor with just lightening, no clearancing, no tip clearancing, no combustion chamber mods. Removing material symmetrical around the rotor. Well, why do we have to rebalance this rotor? Real simple. A factory rotor has factory balance corrections from the factory. These are drill marks or holes, okay, on both sides. When you lighten this area and build a pocket, you're actually machining out those locations, and thus they have to be put back in. So you're removing the factory balancing corrections, so we now have to build them back in. So again, just because this rotor has only been lightened, we absolutely have to rebalance it. Another example would be our combustion pocket modifications. Symmetrically taken off on all three faces, but a little bit of a sort of an awkward machining process, and you have again changed the weight of the rotor. Now, we never do our combustion mods without lightening the rotor. So again, no doubt about it, you would have to rebalance this rotor on its own axis, and similar to this rotor, which is what we call a super light rotor, where we've done the lightening on the sides, but also, if you look at the difference, I don't know if we can get a close-up here, if you look at the difference between the work that's done in here, in the sump side, and here, you can see there's a lot of mill work done all the way around this sump, whereas this one has no work. And these rotors that were sent to us, I noticed, what they did was they drilled a bunch of little holes all the way around. And it's effective. It does help reduce the overall mass of the rotor. But all situations here, you would have to rebalance these rotors on their own axis. And that's what we're going to move to next, is show you how to do that. So again, we're going to do this scalloped and lightened rotor. Again, you can see that the drill corrections from the factory have been almost completely wiped out. You can see some very small traces of them on either side of this rotor, but here it's just flat. So this rotor has been altered dramatically, and we will see how far out it is. So what we're going to do is we're just going to put some lubrication on the bearing. And by the way, we always put new bearings last. So that way, when we're putting in this arbor and we get any marks on the bearing, it's on the old original bearing. And it does not matter what bearing you put in the rotor to actually get the rotor to spin on its own axis on the machine. So we're going to take this rotor and we're going to mount it here on the balancer. And we will turn on the machine, and then we'll install the belt. And then we're going to install the RPM pickup here. And we're going to put a little lubrication on either side of the spindle. And all we have to do is hit our start button on the keypad, and this rotor will start to spin. So if you focus down over here on the keypad, you can see that we have a ramping status and an RPM of only approximately 360 RPM. This RPM will actually increase as it samples. So in the ramping phase, the balancer is sampling and making determinations where it's comfortable to spin the rotor to. And what you'll notice is the more accurate we get the rotor with corrections, the faster the machine will want to spin the rotor. And it typically will sample each rotor at around 1200 RPM in the final phases when we're getting much closer. And the first couple of spins, when the rotor is completely out and nowhere near where it's supposed to be, is when the sampling stage takes the longest and when the RPM increase is the slowest. And so we often have to be patient. And now you'll see the RPM is rising. And again, that means the machine is getting more comfortable sampling and measuring and memorizing the imbalance of the rotor, and will slowly start picking up the RPM to where it will be comfortable to put it into a measuring phase where it takes its final measurements and then records exactly where the corrections need to be made. So now we're getting into the further sampling stages, and pretty soon, yeah, you see now we're measuring and the RPM is closer to 750 RPM. And so what will happen is when this counts down, it'll show us some values. Those are our values, and you'll see the rotor has stopped spinning. The machine automatically stops, and now we're no longer spinning. So in this particular case, it's saying that we have to take 6.1 grams off the left side of the rotor and 7 off the other. Now I've seen worse, especially RX-8 rotors, and I'm talking stock RX-8 rotors that are actually found in road car production engines, which blows my mind. But anyway, so what we do is we rotate the rotor back by hand. I don't know if you can see me spinning this, and I'm lining it up until we get to 42.5. Much like a tire balancer, you bring the item to its top dead center location on the machine, and now when this number starts flashing, that means we have to make a mark here. Now we're almost right at the top, so I have to go right beside the apex tip, and I'm going to write down that it wants to remove 6.1 grams, okay? I'm writing that right on the rotor. And then I continue to rotate the rotor to 43.5, and it says it wants to take out 7 grams there. So I'm going to make another mark here right beside the apex tip and write 7 grams there. And now what we're going to do is we're going to remove this rotor, we're going to mount it to the milling machine and show you how we do the corrections. So we're just going to lock this rotor down to the table here, and now what we're aiming for is concentrated material removal on this tip specifically. Now, if the machine, for example, had asked us to remove the 7 grams here rather than here on the tip, we would split the difference, 3.5 and 3.5. If it was 60% this way and 40 that way, for example, you know, you do something like 5 grams and 2 grams, or 4.5 and 2.5. Okay, so now what we have to do is we have to line up our milling, our end mill, with the factory correction mark, which is a great guide. So what I normally do is I run the machine down and I will rotate the spindle by hand and see how my mark compares to the factory drill mark, and I'm almost bang on the money. I've been doing this for a long time, so I'm pretty good at this, and I'm usually pretty good at determining how much material we will remove. So I'm just going to get some glasses and we'll fire up the machine in a second. Okay, sorry about the break. Had to get safety glasses. Safety's number one rule of thumb around here. So, okay, now that we're ready to go, what we're going to do is I'm just going to fire up the machine. Actually, we're going to put my magnet here, which is what I usually do to catch filings. And actually, interestingly enough, when you do balancing, one of the things you can do, especially when you're pulling off counterweights and putting them on the mill table and bolting them down, and you already have a spec, a measurement of material that you need to remove, a magnet's great because you can drill right through the hole. The magnet will collect the filings, and you can stop when you think you're close, take the magnet and the filings over to the scale and drop them on, and you can see how much material you've removed. So magnet's great. Now it's not great for this because magnet is not going to catch all the filings, but it makes my work surroundings not so messy, and just what I prefer to do. Here we go. The vibration, by the way, is coming from the fact that we're sort of going over top of an existing hole. Now that that existing hole has been wiped out, the mill is nice and smooth and you don't hear a lot of that vibration in the background. So I'm going to take another magnet and remove the filings that are here so I can see the approximate depth of the hole. And from my experience, I can tell you we're close, but we probably need to go a little more. So we're going to take a little bit more material off this corner. And that's going to be good for that one. And now, whoops, we are going to leave that there. Always better to be conservative and not take off the maximum material you think might need, sort of going at the low end of the scale based off of your feeling for the process. And we're going to flip it over and we're going to do the other side. Okay, so we'll be back in a minute. Okay, so we're mounted on the other side. We're exactly equal and opposite to the other tip, which means, again, the concentrated weight wants to come out right at this area, which is good and bad. So it's good for the fact that it's nice to be able to just correct one corner on each side and be done and not have to try and split differences and figure out how you're going to balance the weight across the span of one side of the rotor. The bad part is when you have more tips to spread the required weight removal across, you don't have to worry about going so deep and thus having to make an overlap hole. And I'll probably show you what that is maybe on our second spin. When we have to correct again, we will no longer be going any deeper on that main hole. We will be going off to the side. But this one is only 6 grams, so our hole is going to be a little lighter. Again, I'm going to run this down and just scratch the surface here and see where we are in relationship to the factory hole. Again, smack on the money, so we're going to run it right there. Going to hear it be a little bit choppy again at first here, a little vibration. And now we're past that factory hole, and now the machine is cutting very smooth, very gradual, and we're going to go a little more. I'm going to say, based on my experience, we are probably at the 4.5 to 5 gram area. We're trying to get to 6, but I'm not going to go all the way there yet. I'm going to kiss it once more, and we are now going to spin it before I try and get dead on the money. Okay, so we're going to remove this rotor, meet you back over when we're going to spin it up, and we'll see where we're at. Okay, so the rotor's back on and spinning. It's just taking its final samples and going through the measuring process. And you'll see as soon as it counts down, you can zoom over to the rotor and you'll see the machine stops and the rotor just comes to a halt. Now, one thing we did not show you is we did spin this rotor once already and do a correction. Again, in fact we did 2, and if you look now, we are bang on the money at 0. So now what we have to do is repeat the process to the other rotor, make sure it's at 0, and now we can show you how we measure our weights of our rotors and then spin the rotating assembly to do the counterweight corrections. Okay, so we've weighed the rotors, and the weight that we are trying to simulate for the bob weights is 4,329 grams. So in this case, we're at 4,702 we have to remove. Now what we have to do is we have to do everything in 3s because we have 3 locations of the bob weights for the weight to attach. So we're going to start stripping this off slowly and see where we get to. Now these rotors again are quite light because of the scallops and so on. What you'll notice here is even with our hold downs and these larger weights, we are still above where we want to be. So we actually have to remove these big ones and put the smaller wafers. This is interesting. This doesn't normally happen. There we go. Put the smaller ones on here. Put this back on the scale. Zero that. And put our hold downs back on because that's a guaranteed part of the mass that we're spinning. Go back up to 4329. So what I do is I do this. 1, 2, 3. We're not there yet. I'm going to try 3 more. 43.28. We're bang on the money. We always go plus or minus 1 gram. We're not going to try and dick around and try and figure out how to split one of these washers over 3 spots. So we're going to load this up with equal numbers of brass weights on all sides, which means each corner is getting 3. And then we put our hold downs back on. And there we have our final weight of 43.28. Okay, so now we have to mount these to the E-shaft and mount the rotating assembly to the balancer. So we're going to do the other rotor and bob weight real quick, and we will see you when we're ready to go over to the balancer again. Okay, so we're just going to slide this bob weight down onto the shaft and line it up flush with the bearing, and then we just tighten our set screw. Okay, and then what we're going to do is we're going to spin this over. We're going to put the front one on, and then we will see you on the balancer. Okay, so we've got the shaft and the bob weights mounted on the machine. This is an RX-8 shaft, which are recommended to the customer to use, with some RX-8 gears. And because we're using the RX-8 gears with a large thrust washer, we are going to maintain the large thrust assembly and use a large thrust assembly front weight, which only gives us the option to use either RX-8 or FD. In this case, because the rotors are so light, we want to use the counterweight, which was designed to work with the lighter of the 2 rotors, which is not the FD, it's the RX-8. So this is the counterweight that we're going to use on the front. Now, normally I would start by matching this with a back RX-8 rear counterweight as well. However, this customer had a bunch of counterweights that he sent me, so I didn't have the opportunity to supply him one. So instead of giving him a new RX-8 one, we're going to use the one he supplied, which we glass beaded, inspected, looks like it's in decent shape. So we're going to go ahead and put this on the back, and we're going to tighten the nut up. And then what we're going to do is we've got a box of, here's our flywheel nut, obviously we're going to tighten that in a minute. We are now going to build our front stack. So we've got a couple of custom spacers that we use here to put the counterweight in about approximately the exact location it would be with the thrust assembly and everything behind the front cover in place after it's been torqued. And we're using those spacers, that counterweight, and then of course he's using a 86 to 92 type block, so we're going to use the 86 to 92 type oil pump sprocket. And then we are going to use the standard distributor drive and metering pump gear. And last, what we're going to do after we stick in our keyway here is we're going to put on a front pulley hub. It doesn't really matter what generation, all these hubs are pretty much the same. What we do is we actually put the bolts that hold the external pulley on in, because that's sort of part of the balancing and the rotating assembly as it will exist in real world application. And then the eccentric nut that he will use again will be 86 to 92. So we're going to use an 86 to 92 nut, and we're going to thread that in like so. And then we're going to tighten these, connect our belt, spin this up, and get you back in a minute. So we have everything mounted and the belt's on. We're ready to do its first spin, and let's see where it goes. So we're measuring now. Take a look here. We're counting down, and we are seeing, okay, so that's kind of what I thought. So again, we have a light weight on the front from light rotating assembly of an RX-8, which means we're only asking for 22.3 gram correction on the front. Now on the back, it's asking for 61 grams to be removed, and there's a good explanation for that. So as I said, this customer sent us a few different counterweights. I actually weighed this back counterweight when we went to break, and this counterweight told me it was from a second generation. So although these are second gen rotors, we've made them much lighter than any factory rotor that would ever be available in a production engine. So if we zoom back, you see that we're now at 20. We have to remove 61 grams from here. Now normally what you would do with light corrections is we would leave this counterweight on the shaft. We would spin our mill head, which is designed to line up with the center of the V-blocks, and we would do our drill corrections right on this weight. The reason we can't do that is because we're not going to be able to accomplish 60 grams of weight somewhere in this top 15 degrees worth of space. We're going to have to hit it heavy right on the face with a large slot drill, not just a 1/2 inch drill bit. So we're going to remove this, put it on the table, and show you those corrections. Okay, so counterweight's mounted to the mill table. We've got the counterweight marked in the 2 spots where we want to drill some pretty serious corrections. Okay, so we're going to go quite deep. I'll plop our magnet here, and here we go. So we've got a hole that's about 2/3 of the way through this counterweight, okay? And it is very possible we're going to end up going right through. What we're going to do is we're going to drill the next hole over here, then we're going to remove the weight, put it on the scale, and see how much material we remove from the original 1,852 gram weight. And we'll bring you back shortly. Okay, so we have drilled our counterweight literally right through in 2 places, and a small correction in the middle to get our approximately 60 grams, or about 55. If we have to do 5 more grams correction, we can do it on the V-blocks with the mill head drill bit here, which is what we're going to have to do with the front one anyway. So we're going to spin this up real quick and see where we stand. And if we're close, we will immediately spin this mill head around and take our front measurement and do the front corrections, and then go back to the back one. That's the proper order. We're going to leave the rear one alone until we've pretty much zeroed the front. So here we are measuring up, and let's see how close to 0 we are on the back one. Okay, so we are within 6 grams on the back, but we have to remove 16 from the front. So let's get the mill head ready, and we'll see you in a minute. Okay, so what we've done is we've changed the mill head to the drill chuck. We're going to swing this head of this mill right around like this until we are lined up with our front counterweight, which is about here. Okay, so what I have to do is lock down the mill head so it's stable. Lower it down actually first, lock it down, and then we're going to use the airlock, which you'll hear and see in the next shot. So we're perfectly located right smack in the middle of our front counterweight. Be right back. Okay, and actually what we've done is we've locked down the mill head so we've got enough room to correct also the taller, larger radius rear one. Okay, so you'll see we can't move the mill head until we unlock the mill, and we gradually slide that across, and we now have to get our front one right there. And that's where we want to be. And again, with this airlock, we can't move. It's a very aggressive airlock. It will not allow this 750-pound mill to move a millimeter. Okay, and we're going to do our corrections right where the factory holes were, and we're going to be doing 2 consecutively, going down about 1/3 of an inch. So we'll be right back. So we have a little cardboard template here, which is designed to protect the filings from going all over the lubricant on the journals. We're lined up with our first hole. We're going to drill right through the magnet to catch our filings. We're going to turn this on. We're going to slowly take out some material. Now the machine actually does tell us what depth of a hole would bring us approximately to that weight that we're looking for. And I'm doing that by watching my slide scale on the milling machine. So that's hole number 1. That's just our RPM gauge that fell off. It doesn't matter. It's just a magnetic gauge. And we're going to stop right about there. Now again, I can take these filings and bring these over to my scale, and I can see that I have milled out approximately 11 grams of filings, which should put us in the ballpark. So we're going to reconnect everything and do a test spin, and our last corrections will be probably a little bit more on the front, and the final correction on the back, and possibly one more back to the front. See you shortly. We're going to spin this up one more time and see where we stand since our front corrections. And I'm guessing we have about 3 left. Just cool these down a bit. And the machine should speed up here to about double speed. It's going much faster. We're at about 800 RPM. And we are measuring now. Let's see where we end up. Okay, we're very close. We got 4.8 grams on the front, 6.5 on the back. We are going to actually do a correction on the rear, which is the heavier side. So we're going to bring this up to 9 till that's flashing. So we're going to take out 9 grams, 6.5 grams right here at 9 degrees. And we'll get set up and we'll bring you back. So we're going to check the amount depth. It says 0.26 of an inch, so we got a 1/4 inch to drill down. We're going to bring this down. Call that 0.2 of an inch. 0.26. That's exactly where it asked us to bring it to, was 0.26. So we're going to try that, and then we will see if we need to correct the front. Be right back. And we are, look at that, we're 0 on the rear. We have one last correction on the front to do. So we'll set it up and bring you back one more time. Okay, last correction. Amount depth, 0.17 inches. Shouldn't be too hard. I would say we are close to there now. Let's go a little more. 4.3 grams. I would say that's almost you smack on the money. Let's weigh this. Yes, that is exactly 4.5 grams. So we're going to hook up our RPM dial gauge and spin this one more time and see if we hit it. Again, the closer we get to being accurate, the quicker the machine samples and the faster the RPM it will spin, and the quicker we will get an overall reading. So once again, it's ramping up very fast. We're over 800 RPM there. And it's just doing its last bit of sampling, and now we're measuring. Let's see what happens here. Okay, so we're zeros on both sides. That is a wrap, ladies and gentlemen. That is how you balance a rotary engine and how you zero it on either side to perfection. And that's again what we aim to do around here. I hope you've enjoyed it, and hopefully we'll see you real soon.